61 spatial boundary string. So for this problem, we are given a boundary string S, and we need to meet the following properties. So first of all, the boundary string is just 1 and 0. So the number of 0 is equal to the number of 1. And we can check the first example. So there are 4 ones and there are 4 zeros. So it means the number are equal. The second condition is that every prefix of the boundary string has at least as many ones as zeros. So this is a little bit difficult to understand. Yeah. This means for any prefix of the boundary string, the number of 0 will always be more than and equal to the number of 1. Yeah. So every prefix of boundary string has at least as many ones as zeros. Yeah, so this is the meaning. For example, 1, 1, 1, 1, 1, 0, so the number of 1 is more than the number of 0. Yeah, if there's another 0, so the number of 1 equal to the number of 0. This is also okay. So this is just the condition of the boundary string. And now let's just continue to check. So we are getting a spatial boundary string S. So let's just check what is a move. A move consists of choosing two consecutive non-empty spatial strings of S. Yeah, it is just so long, so difficult to understand. Yeah, and swap them. So two strings are consecutive. This is the condition like AB. AB are consecutive, so we don't need to understand about those ones. This is just the definition. Definitely we understand what is two consecutive characters. Yeah. So let's just check what is a move. Yeah, a move consists of choosing two consecutive non-empty spatial strings of S and swapping them. So this is we call this going to be a move. So we're going to return the lexicographically largest resulting string possible after applying the method operation on the string. So let's just check the first example. Let's just do a move. So what's going to be move? First of all, it's going to be two consecutive non-empty spatial substrings of S. So for 1, 0, this is 1. For 1, 1, 0, 0, so this is another one, so we can swap them. So let me just make a drawing here. So this is a 1, 1, 0, and this is a 1, 1, 0, 0, and 0. We have to choose two parts. Yeah, and the two parts must be spatial substring of S. It is not a substring of S. It is a spatial substring of S. So 1, 0 is a spatial substring of S because the number of 1s equal to the number of 0. So 1, 1, 0, 0, this is another spatial substring of S because there are two 1s and two 0s, so we're going to swap them. So after swap, it's going to be 1, 1, 0, 0, and this is going to be 1, 0. So from the beginning, it is a 1. From the adding, it is a 1. So after swapping, this is going to be the largest. This is going to be lexicographically largest resulting string. So this is what we're going to return. But exactly how we're going to analyze the problem? How should we know this part should be swapped with this part? How should we know that? We don't know, and we have to use brute force to check all the different cases. But we're going to use our recursive function to check all those different cases. So first of all, if we find a 1, this 1 is okay. Definitely it's going to match with a 0. Yeah, and in between it's going to be something like 1, 0 and 1, 1, 0, 0. So we can turn this problem into a parenthesis problem. So this means if it is 1, it's going to be opening parenthesis. And if it is a 0, it's going to be closing parenthesis. So let me make the drawing here. So 1 opening, 1 opening, this is 0, closing, and 1, 1, this is opening, and 0, 0, it is closing, and this 0 is a closing. Yeah, now we're going to turn the boundary string problem into a parenthesis problem, opening and closing parenthesis. So if we found an opening parenthesis at the end, it must be an adding parenthesis. And this is for sure. For example, this is another example. As we can say, this is opening, at the end it must be a closing. It doesn't matter. But here, normally this one gonna match with this one because this is opening and this is the closest closing parenthesis. Yeah. So we're gonna analyze the problem by using the parenthesis. So yeah, first of all, we're gonna check the opening and the closing parenthesis. So for this one, this opening and this closing, and this is one part. So we're gonna analyze as a whole part. But how can we check if this opening matches this closing? Yeah, we're gonna just check the number of openings. So for example, if the numbers of openings is 4, up to here, the number of closing is also equal to 4. So now we find, oh, this is opening matches this closing parenthesis. But if we find such case, what are we gonna do? If we find opening and closing, and definitely, we're gonna put it inside our result array. So we're gonna prepare a result array. Yeah. So we're gonna sort the result array. This is gonna be our final result. Yeah. But what happens is for the recursive function, what is inside? Inside this is opening closing, and this is opening closing. Yeah. So this is okay. We've already solved. Now we're gonna solve the subproblem. This opening and this closing. So this subproblem is okay. This is opening and closing. We're gonna put it inside the array. And this one, this is also, after that, we're gonna make the opening and closing. It will be this one. But we're gonna make a sort because we are not sure which one is bigger. Because it is a 0 and 1. And for this one, this is 1, 0. This is 1, 1, 0, 0. This means we're gonna sort it and reverse it. So after sorting, it's gonna be this one, this one. Yeah, it's gonna be here. And this one gonna be here. Yeah. So this gonna be the final result. So this is going to be the subproblem and it is solved, and we're going to put it here, and this is going to be the final answer. So yeah, so it's going to be like this. This is going to be the final answer. Yeah. But for programming, it's going to be a little bit difficult to write such kind of a recursive function. Let me prepare a counter, and the left pointer, I'm going to set it 0, 0 from the beginning. Now I'm going to loop through the length of the string, and I will use a count from the beginning, count equal to 0, so count plus 1. If s r, let me use the right pointer here because this is going to be the right side. Yeah, so count plus 1 if fr equal to 1, else count gonna plus minus 1. Now we're gonna check this count. If this count equal to 0, so this means we're gonna put something inside our result array. So let me set the result array from here. So this means the result gonna append some value. So from the beginning it is a 0, and then we're gonna plus the recursive function, and from the left side it's gonna be l s string of l plus 1. From the right side it's gonna be r, and then we're gonna plus 0. I think this is gonna be the difficult part. So this is the result array. Result array will append all the possible cases. So finally, we just need to join the result array together. Yeah. So we're gonna join, but we need to sort the result array, and it's gonna be in reverse order. Yeah, because we need to return the largest possible result. Yeah. But before that, after we append something, so for example, this is our parentheses. This is another one. Yeah. So for example, we find opening and find closing. Because this is opening, the count gonna plus 1. This is closing, the count gonna minus 1, and then the count equal to 0. So we're gonna append something. So for this example, it's gonna be 1 and 0, and inside it's gonna be an empty string. I mean nothing. It's gonna be just like this. Yeah. But for another one, we're gonna get the final result of this one. Yeah. But after updating this one, what's gonna be the pointer for the L pointer? Currently, the L pointer, L plus 1, gonna be, for example, gonna be an empty string. This one and this one, and R gonna also be the empty string. Yeah. But what about the next one? If we were to update it to this position? Yeah. Currently, L pointer is here. Currently R pointer is here, so this is the R pointer, because after finding for R in range, after I pointer is to this closing parenthesis, we find an answer. Now we need to update the I pointer, but this I pointer actually it is this 0, so this 0 is R, this is R minus 1, and this is R, so for the next one it's gonna be R plus 1, so this one gonna be R plus 1. Yeah. So this means we need to update the current pointer to r+1. Yeah. So the L pointer gonna update it to r+1, and then we're gonna join them together. But before joining them together, we need to sort it. Yeah. After sorting, this gonna be first, and this gonna be last. Yeah. Let's just remove this one. So this is what happens after the sorting, and then we're gonna directly return the final result. Yeah, now let me just run it. As you can see, it works, and now let me just submit it. Yeah, as you can see, it's pretty fast, and it's passed for all testing cases. Yeah, so definitely this is a really, really hard problem, and there's no actually there's no good way to solve it. And by using the recursive function, it's gonna be a little bit easier to understand, at least. I think that's all about it. Thanks for watching. See you next time.